Welcome back everyone to the next part, part 3 of Weyl calculus, semiclassics using quantization procedure. So now that we have defined the quantization, the other task to prove the Egorov theorem was to relate the commutator of operators to the quantization of the Poisson bracket. And the way you do this is by introducing the so-called Weyl product. So the Weyl product is, in a sense, the pullback of the operator product on the level of functions on phase space. So how do you do this? Well, what you do is you define the product sharp to be the best way is to do it like that. The quantization of the Weyl product of f and g is by definition the quantization of f, which is an operator, times the quantization of g. So this is what you do. And that is the central object that we will be concerned with here. So a priori, this is a very abstract definition, and we don't really know whether it is even defined for for what functions it is well defined. So as usual, let us start on the space of Schwarz functions. This is for two reasons. One, it allows us to avoid a lot of technical complications that we run into if we were to define it more broadly. And the second thing is it allows us to rigorously establish the correct equations, which can then be extended by, for example, by using oscillatory integrals to broader classes of functions. So there are two paths to actually compute the Weyl product now. The first path is to use the inverse of Weyl quantization, which is related to the Wigner transform. So we will talk about the Wigner transform next. But this is not the path that we choose today. I mean, this would be perfectly doable, but for this simple equation, we can actually just use direct computation. Let me give you the solution first. And then as part of the proof, I will explain to you how to get there. So the equation is as follows. If we evaluate the Weyl product of f and g at x, then this is a prefactor of 2 pi times integral in capital Y. So capital letters are phase space variables. Then we have e to the I sigma of x and y plus z. Then we have e to the I epsilon half sigma of y and z. And then we have the symplectic Fourier transform of f in y and the symplectic Fourier transform of g in z. Of course, there are equivalent formulations that you can arrive at, for example, by writing out these symplectic Fourier transforms and combining the phase factors in many different ways and canceling some of the phase factors out by integrating out the variables. You get some delta functions and so on and so on. But this is certainly one form, one of several equivalent forms. And the advantage is that this form allows us not only to analyze the equations in a very simple fashion, it also highlights the structure in a very simple way, and it allows us to do an asymptotic expansion of the Weyl product. So, but one thing at a time. So the phase factor, so this first phase factor is just a symplectic Fourier transform in y and z evaluated at x. So if this factor here were absent, we would just have f sigma squared of f evaluated at x times f sigma squared of g evaluated at x, which is just the pointwise product of f and g evaluated at the point x. So this tells us that it is actually this factor here that makes the Weyl product non-commutative. So of course the Weyl product, because it is defined in terms of the operator product, inherits the non-commutativity of the operator product. And it is precisely this factor in the middle that makes the Weyl product non-commutative. And the other thing is, so this is point 1. Point 2 is that the Weyl product, seen as a map from the Schwarz functions times the Schwarz functions on phase space to the Schwarz functions, is continuous. So of course, because this is a mini course, we will actually not prove 2. Not because it's conceptually very hard. It is not. It's very tedious, and you can already see how the game is played. What you need to do is you need to first make sure that this here is well defined as an absolutely convergent integral, which it is, because Fourier transforms of Schwarz functions are Schwarz functions, and these are just phase factors. So you can pull absolute values inside, and then you just get, you arrive at the conclusion that this is well defined. But you can do more. You can even estimate the supremum in X. And that is quite simple, because the X dependence is here. And by taking absolute value, you get actually rid of this. And for the other semi-norms, well, you have to justify that you can exchange integrals and derivatives and so forth, which is, let's say on this on your level is quite standard and, you know, just quote unquote left as an exercise to the reader. So let me focus on the first point, and I think there is an important auxiliary lemma or an auxiliary fact that I will also not prove, but is easy to see. Namely, if you take the product of w of y and w of z, so remember this is the Weyl system, then this is equal to e to the I epsilon half sigma of y and z times w of y plus z, where of course w of y, as a reminder, so this is w of small y and eta is equal to e to the e to the minus I sigma of y, q, and p, which is the same as e to the plus I y times p minus eta dot q. So you can just prove this by applying the left-hand side to a function, a Schwarz function or an L2 function, evaluate this function at x, and then, you know, just rewrite this as a system applied to psi, and you see that you're missing this phase factor here. So this is relatively easy because it follows from direct computation. And once you understand this, the proof of the proposition, or let's say of part 1, is also relatively easy, because what you do actually is you just write out the right-hand side from the definition of the Weyl product, and then you say, okay, what I get here is, first of all, I get the correct prefactor. I also get two integrals over phase space. And let me collect the prefactors. One is f sigma of f evaluated at y. The other one is f sigma of g evaluated at z. So I'm just plugging in the definition of the of Weyl quantization. I'm doing really nothing. This is really, really easy. And then I have the product of wy times wz. By the auxiliary lemma, this here can be written out as e to the plus I epsilon half sigma of y and z. So you already know where exactly this phase factor that makes the Weyl product non-commutative comes from. And then you have w of y plus z. And then we shall make a coordinate transformation where we replace y plus z by z prime. So this is a coordinate transformation in z. So I have the integral over capital Y, and then I have the integral over z, capital Z prime. So I'm leaving the momentum variable unchanged, but let me just relabel it for convenience. And what I get is, well, I'm doing nothing to y, so I'm just copying. And then to connect, to make the correct substitution here, I have to replace z by z prime minus y. And then I have to multiply with the prefactor. And then I have a wz prime. Ah, okay, I'm missing something here. Actually, it's not wrong what I wrote once I put a prime in here. But let me do this nonetheless. Since we're dealing with absolutely convergent integrals, I can just do the following magic here. I can reverse the order of integration. And then I can just put brackets around it. And then I see, well, up to a factor of 2 pi to the d, because we have a factor 1 over 2 pi to the power 2d here, this is equal to the symplectic Fourier transform of f while g evaluated at z prime. But because the symplectic Fourier transform is its own inverse, what I can now do is I can just compute the symplectic Fourier transform of the term in parentheses, and I'm also going to borrow a prefactor of 1 over 2 pi to the power d. So this implies that f while g evaluated at x is equal to the symplectic Fourier transform of the term in parentheses. So what is the variable that we are transforming? Well, let's think about it. Well, it must be the z prime, right? So we have to replace this by a dot. So we have e to the I epsilon half sigma of y and dot. So this is the variable that we are computing the symplectic Fourier transform in, minus y times f sigma of f evaluated at y times f sigma of g evaluated at dot minus y and then I'm evaluating everything at x. So let's just write it out. And what we get is, first of all, a prefactor of 1 over 2 pi to the power 2d. So one is taken from here. The other one is donated from the symplectic Fourier transform. And let me just reuse the variable z now, or z prime. let me write out the phase factor from the symplectic Fourier transform. So I'm Fourier transforming in Z prime, but I'm evaluating at X. This is important. Then I have the twisting phase factor, e to the I epsilon half sigma of epsilon and of y and Z prime minus y. And then I have f sigma of f evaluated at y and f sigma of g evaluated at Z prime minus y. And now what we will just do is we will undo the variable substitution. And what we arrive at is just the formula that I claimed was the correct one. So now let me just reorder alphabetically because, you know, it's more beautiful this way. So the first factor here, Z prime has to be replaced by y plus z, which is exactly the right thing. Then we have e to the I epsilon half sigma of y and z. And then we have the symplectic Fourier transforms of f and g evaluated at y and z. And that's the correct equation that we claimed we needed. So well, that's just an estimation exercise of semi-norms. And again, I think that is not very suitable for a mini course, but it's quite standard. All right, so now let's get a step closer to actually proving the second main ingredient of the Egorov theorem. And this is the asymptotic expansion of the Weyl product. Of course, in the semi-classical parameter epsilon. And it just reads as follows: for all natural numbers n and n, we can include the 0. We have the following. Well, f while g is equal to the sum from small n starting from 0 to capital N, epsilon to the power small n, and then you have terms which are explicitly given. So this is f while g in parentheses n, so this is the nth order term, and then I have order epsilon to the power n plus 1 plus a remainder term that depends on the order and obviously on the two functions f and g. And of course, as this notation implies, is that the remainder is big O of epsilon to the capital N plus 1. So that's the whole point. Of course, this expansion holds for Schwarz functions, at least initially, and we can extend it. And all of these terms are continuous functions for Schwarz functions. And this is now the main point. In principle, we can give explicit expression for all of these terms order by order. They're relatively simple, but for the sake of simplicity, let me just focus on the first two. And of course, let's say the 0th order term and the first, the subleading term, the first correction. Well, the 0th order is just a pointwise product of functions. So f times g, that's the pointwise product of functions. And the first order correction, well, drum roll please, big surprise, is minus I divided by 2. Remember, I've factored out epsilon here. So this here is the order epsilon term. So it's minus I divided by 2 of the Poisson bracket of f and g. And just a reminder, the Poisson bracket is just the psi gradient of f dot the x gradient of g minus the x gradient of f dot the psi gradient of g. This has an immediate corollary which answers the question that we posed in the first part. The first point is that the Weyl commutator of f and g, so this is exactly defined how you think it is defined. So it's just f while g minus g while f. And this later quantizes to the commutator in the operator sense of op f and op g. This is equal to minus epsilon I, and then you have the Poisson bracket of f and g plus order epsilon cubed. So let me emphasize that this is a cube. So a quick prooflet, why does the Poisson bracket appear here? Well, the Poisson bracket is antisymmetric. So the Poisson bracket of f and g is minus the Poisson bracket of g and f. So I get a minus I over 2 contribution, and then I have the Poisson bracket of f and g minus the Poisson bracket of g and f, which is twice the Poisson bracket of f and g. And 2 times I divided by 2 times 2 is I. So that's where this comes from. Why is the error order epsilon cubed? Well, it turns out that all of the even terms in epsilon are symmetric, meaning that they cancel exactly. And the next term in the asymptotic expansion of the commutator is cubic. The next one after that is quintic. Then you have epsilon to the 7, epsilon to the 9, and so forth. And so the point here is that, okay, of course, it is true that order epsilon cubed is also equal to order epsilon squared. Please only read this in one direction, not in both directions. So what we get is actually something better than what we need for the proof of the Egorov theorem. And then there's point 2, which is a quick consequence, namely I divide by epsilon. And now it's the commutator in the operator sense of op f and op g. This is equal to the quantization, the Weyl quantization of I divided by epsilon times the Weyl commutator, the Weyl commutator of f and g. And by point 1, this is minus I epsilon, which cancels this prefactor here exactly, times the Poisson bracket plus a term of order epsilon cubed. But of course, we have a prefactor 1 over epsilon. So what we get here is the Weyl quantization of the Poisson bracket f and g plus order epsilon squared. So again, this is one order better in epsilon than we actually need, but you know, we'll take it. We get it for free, so we'll take it. Of course, I'm being intentionally vague here. Initially, these facts hold for Schwartz functions, but later on we will extend the Weyl product to more general functions, and then it's relatively clear that these facts also hold verbatim. So let's prove the asymptotic expansion, but this is really, really easy because we've chosen the right form of the Weyl product. So let me just copy and paste the explicit equation. So we start with this. Let's just delete the superfluous annotations here. Okay, so the only epsilon dependent part is this one here. And the exponential function has a Taylor expansion, which is absolutely convergent everywhere, super nice. So all we need to do is expand this term, which I call the twister. So I'm just writing out the Taylor expansion up to nth order. So I'm choosing some capital N. And even though I could choose n equals to infinity, but let's just do a finite expansion. Then I have an epsilon to the power n. And then I have to take I to the n divided by 2 to the n times 1 over n factorial times, now let me write out the sigma, which is just eta times z minus y dot zeta to the power n. And then I get a remainder, which are called small rn. Oh, sorry. Let me factor out the epsilon. So it's r capital N. And this depends on capital Y and capital Z. There are many ways to write this remainder. I think the most useful one is to use an integral formulation, because then it's clear that this term here has a polynomial of degree n plus 1, capital N plus 1. This will be important if you want to consider the Weyl product between Hermander symbols, because there you really have to do some bookkeeping. For Schwartz functions, that's not so crucial. And then, okay, it's relatively clear. This term here goes into the nth order term of f while g after incorporating it into the integral, and this here leads to the remainder term capital Rn of f and g. So I think that's relatively clear. So this is a finite sum, so I'm there's nothing to worry about in terms of convergence or anything. And I obtain an explicit equation for the nth order term, which is still an integral. Let me use the magic of copy and paste again. Okay, let's try this again. I hope my magic is not exhausted for the day. Okay, nope, still works. So I need this part only because I factored out the factor of epsilon. And then I have this here. So let's analyze the term real quick. So this here is a polynomial of degree 2n. So this is a this is quadratic, this is quadratic. And then I'm taking the nth power of that. So this gives me just a sum of monomials in small y, eta, small z, and zeta. So what we need to do is, well, what can we do? Well, we can convert these guys into derivatives, right? Because for Schwartz functions, we know that, for example, if we have yj multiplied with f sigma of f evaluated at y. If we write this out, then the monomial factor in y becomes a derivative in momentum in eta. So this is the same as, well, minus I. So the factor of I is clear, and then you have to figure out the sign. And if you look at the equations, the right sign is a minus. And then you take the symplectic Fourier transform of the momentum derivative in the jth component of f and evaluate that at y. And of course, similarly for eta, z, and zeta. So this means that this factor here just becomes a bunch of derivatives of f and g. And for the remainder, well, it's also very easy. If you're really lazy, what you can do is, that this here is well defined on the Schwarz functions. And this remainder is just this guy minus the finite sum of all the terms up to order n. All exist, are nice, etc., etc., all give Schwarz functions. So this way you can also control the remainder. So this is how we control the remainder. And to see how to reduce this integral expression to a pointwise expression, let's consider just the first two terms, and then, if you want, as a small homework exercise, you can do the others. Well, for n equals to 0, if we evaluate at x, we get I to the 0 divided by 2 to the 0 divided by 1 over 0 factorial. So the prefactor is just 1. Times, now let's again copy and paste. Times this here, and times this here. Of course, the n was not supposed to go on this journey. And if you look at it again, the integrals in capital Y and capital Z factor, in fact, they just give us f sigma squared of f evaluated at x times f sigma squared of g evaluated at x, which is just f of x times g of x, the pointwise product of f and g as I claimed. Now let's do the first order term, which is dispatched in a similar fashion. Let's do the prefactor from memory. So it's I to the power 1 divided by 2 to the power 1 times 1 over 1 factorial. So this is equal to I over 2. So there's no minus sign yet. The minus sign is still missing in action, but it'll come. We'll get there soon enough. And now what we need to do is we need to just add this prefactor here, but let me write it out in terms of a sum from j equals to 1 to d of, well, let's go back, eta dot z, so it's eta j zj minus yj zeta j and now by what I just said before is that, okay, the eta j becomes the symplectic Fourier transform of f in yj. The zj becomes the acts here on the g as a derivative in zeta j. And similarly for the second term. And the prefactor is a minus I squared. So what I get here is minus I squared times I half. And then I have the symplectic Fourier transform. Let me write out the sum. So this integral collapses because you just end up with the symplectic Fourier transform squared. So this is the symplectic Fourier transform squared of dyj of f evaluated at x, f sigma squared of d zeta j in g evaluated at x minus, well, now the roles of the derivatives exchange. So here I have the eta j derivative of f times the zjth derivative of g. So this here just becomes the x gradient of f dot the psi gradient of g. And this minus the psi gradient of f dot the x gradient of g. And this agrees with the Poisson bracket up to a global sign. So this is where the minus sign comes from. So this is minus I over 2, the Poisson bracket of f and g evaluated at x. And this is exactly what we claimed. And then the again, as before, the continuity I leave that as an exercise. So continuity, of course, with respect to the Fréchet topologies of initial and target spaces. All right, so this is the result for Schwartz functions. And if you want to extend it to more general classes of functions, then, okay, that's straightforward. I don't want to say easy because, okay, it is a little bit tedious, but it is straightforward in the sense that, you know, there exist standard techniques, namely oscillatory integrals, that explain how to do it. And underlying this is, of course, again, an extension by duality. So I again refer to the excellent article by Mantoyu and Purice from 2004. And this is best explained in the part where they explain also how to treat magnetic fields. But the construction, of course, also holds for the special case B equals to 0. So this is very nicely explained. So again, you start with an extension by duality. And oscillatory integral techniques. And let's say for the purpose of the semi-classical limit, let me just state the following theorem. I recall that S, M, rho are Hermander classes of order M and type rho. So you can consider the Weyl product of two Hermander symbols of orders M1 and M2, which are of course real numbers, and this maps onto a Hermander symbol of order M1 plus M2. And this map is continuous. And then, of course, you also have an asymptotic expansion in the following sense. Probably it's simply better to do this on the next page. So cut and paste. Here we go. Okay, so we have an asymptotic expansion in the following sense. For any Hermander symbol F of order M1, and G being a Hermander symbol of order M2, their Weyl product admits an asymptotic expansion in the following sense. Well, first of all, we can pick a capital N. Okay, let me write it out with symbolic notation first. Let me just move this. So for an asymptotic expansion, you also use this equality. This is not an equality. This is like a bent equality sign. And it means, well, that the expansion is asymptotic, meaning that the sum need not be convergent in any usual sense. But nevertheless, asymptotic expansions are useful and give us good results. And what we mean by this is for any capital N being a natural number including 0, we can write f while g as the sum from 0 to capital N of the single terms plus a remainder term so this is just the sum plus order epsilon to the n plus 1. So let me just copy and paste this. And now the important point is that each of the terms must lie in a specific symbol class. So f, the nth order term of the expansion, lies in, well, S m1 plus m2 row. But now, because you have n derivatives in momentum, you have to subtract n row. And of course, the remainder term, Rn, is a Hermander symbol of order m1 plus m2 minus capital N plus 1 in parentheses times rho. And all maps, well, the nth order terms plus, of course, the same for the remainder, they are all continuous. Okay, so I think if you believe point 1, so I'm not going to even attempt to prove this, but if you believe point 1, then I think at least this fact here should be fairly simple to see. And it just comes from the fact that if you inspect the this polynomial here, you see that you always have, if you take the nth power, then you always have an nth power of derivatives, which means by definition of Hermander symbols for each momentum derivative, of which there are exactly n, you get an improvement by rho, which is why you have to subtract n rho. And for the remainder, well, you have capital N plus 1 derivatives in momentum, which is why you get this here. So this is, without giving a proof, this is at least stating why this should be true. All right, and with that, we have overcome the second big obstacle in our proof of the Egorov theorem. Next up is the definition of the Wigner transform.